Okay, the final subtopic for acids and bases is the pH scale. And to be honest, this is partly about the pH scale and it's partly about some other stuff, but that's just the way it's organised in the subject outline. Let's get into it. So the pH scale is a logarithmic scale that describes the concentration of hydrogen ions in aqueous solutions. Solutions with pH less than 7 are acidic, solutions with pH 7 are basic, with pH greater than 7 are basic, and solutions with pH equal to 7 are neutral. And it talks about how we can calculate pH. And we're going to do that in the next slide. Firstly, we will talk about some of this stuff at the bottom. Carbon dioxide dissolves in rainwater to form carbonic acid. We've actually already seen that in the previous video, which is a weak acid giving rainwater a pH of about 5.5. So rainwater, because of the carbon dioxide in the atmosphere, is slightly acidic. Now, oxides of sulfur and nitrogen are also released into the atmosphere through the burning of through the use of internal combustion engines and the burning of things like coal that contain particularly sulfur. There's also some industrial processes that make fertilizers and that sort of thing that also release nitric oxides that lead to acid rain. So what we need to do is just understand the chemistry of these processes. So we've actually already in the previous video talked about the reactions of these chemicals with water. Well, not all of them, but most of them. So for example, carbon dioxide will react with water to form the carbonic acid. Then, and if you like, this is the reason it's acidic, is that it can release hydrogen ions. That carbonic acid can release hydrogen ions when it's put in water to form H plus the bicarbonate ion. And it could also release 2, or that bicarbonate ion can still then act as an acid or a base, if you remember, because it's amphiprotic. I talked about that in a previous video as well, to release another hydrogen ion plus the carbonate, leave you with the carbonate ion. The sulfur dioxide will react with water to form sulfurous acid. Again, we talked about this in a previous video. Sulfurous acid is a strong acid. That means it donates all of its hydrogen ions. We've talked about that previously. So when that's put into water, that will tend to donate both hydrogen ions and leave us with a, not sulfate ion, a sulfite ion. That's got a 2 minus charge. I'm making lots of mistakes here. Sulfur trioxide will react with water to form sulfuric acid. Again, sulfuric acid is a strong acid, so when it's put into water, it will release all of its hydrogen ions, so both of them, and leave us with the sulfate ion. Nitric oxide is a little bit more complex. NO2 plus H2O doesn't form H2NO3, so it doesn't follow that basic pattern. It forms HNO3 plus HNO2, and I think to get your balance there you need to have 2 NO2s. I'd never expect you to remember that reaction. It's a bit of a confusing one. However, the reason obviously that it makes the rain acidic is HNO3 is a strong acid. So when that's reacted with water, that releases its hydrogen ion and forms the nitrate ion. And this other one here as well will do the same thing, but we won't worry about both of them. So that's the reason all of those compounds make the rainwater acidic. As I said, this probably better fits in terms of reactions of acids, but I'm just going with where it is in the subject outline. So I mentioned some of these before. What are some of the sources? The sources of this of CO2 emissions are obviously burning fossil fuels. Sources of nitric oxides can be also from car engines. You also get nitric oxides reacting when you get lightning. Lightning produces huge amounts of energy, and it makes the nitrogen atoms and the oxygen atoms react together to form nitric oxide. It's a similar process happens in the car engine. We cover all this in year 12 physics, so I'm only going to do this very briefly now, just to make you aware. Burning fossil fuels, well, coal is a fossil fuel, so I guess I've already covered that. So what are some of the solutions? Obviously, if we stop burning fuels, that will have an impact that will help. But the other thing, which I'll mention now, but we cover the chemistry of next year, is the catalytic converter. Catalytic converter that's in your exhaust on your car actually helps stop some of these emissions that lead to particularly the nitric oxides being released. So that is, maybe if you're interested, something you can have a look at, or if you're not so interested, you can wait until next year and learn about it next year. So yeah, that's the stuff on the acid rain. That's why these compounds make the rain acidic, because basically they react to form acids, which then can release hydrogen ions. And just a really brief intro into the sources of those chemicals and some of the solutions to prevent them getting into the atmosphere. And that's stuff that you can easily research as well. I think that will do for this part. Let's get into the next slide where we actually talk about the pH scale, which is the topic of this video. So, the pH scale. Firstly, the pH scale is a logarithmic scale. What do we mean by a logarithmic scale? A logarithmic scale means if we have a change of 1 in pH, that reflects something that is a 10 times stronger or 10 times weaker. So a solution with a pH of 1 is 10 times more acidic than a solution with a pH of 2. A solution with a pH of 3 is 100 times weaker than a solution with a pH of 1. So a change of 10 means only a change of 1 in pH. In a sense, logs come from this idea, because I know a lot of people haven't covered logs in maths, that if we think, 100 equals 10 squared, 1,000 equals 10 to the power of 3. If we went to 1 million equals 10 to the power of 6. So the log of these numbers is whatever number you need to put 10 to, whatever indice or power you need to put 10 to get that number. So, what do I mean by that? The log of 100 is equal to 2, because 10 to the 2 equals 100. The log of 1,000 is equal to 3. The log of 1 million is equal to 6. So this is a very brief recap of what logs mean. So to calculate pH, we need to know minus log of the hydrogen ion concentration. Work it out with a calculator. So if we have a solution that has a concentration of 0.001 mole here per litre hydrogen ions, pH equals minus log to the base 10 to the concentration of hydrogen ions equals minus log to the base 10 of 0.001 equals, put it in my calculator, just got to press the buttons in the right order, equals 3. So log of that number is minus 3, but minus a minus makes it a plus if you're following along on your calculator. So that's how we work out the pH of an acid. Hopefully with a bit of practice that's fairly simple. Now if we want to go the other way, if we want to know the hydrogen ion concentration, because we know the pH, we use this formula here. Concentration of hydrogen ions equals 10 to the minus pH equals 10 to the minus 4.5. Put that into our calculator and we get press the buttons right, 3.2 times 10 to the minus 5 moles per litre. Now, it gets slightly trickier when we look at the pH of a hydroxide solution, because we don't have the hydrogen ion concentration anymore, we have the hydroxide ion concentration. And what you can see though from the formulas over here is the relationship between pH and pOH, and also how we work out pOH. So the pOH in this case is equal to minus log to the base 10 of the hydroxide ion concentration, which in this case is equal to 1, and then pH is equal to 14 minus pOH, which is equal to 14 minus 1, which is equal to 13. Hopefully that's reasonably self-explanatory. And if we want to work out the hydroxide ion solution of a pH 12, well, to work out hydroxide ion concentration, up here we need the pOH. We know that pH plus pOH equals 14, therefore pOH equals 14 minus pH. So we go pOH equals 14 minus pH. Yeah, 14 minus pH equals 14 minus 12 equals 2. Now we can plug it into this formula here. Concentration of hydroxide equals 10 to the minus 2 equals 0.01 moles per litre. So that's how we do our pH calculations. And we've just got the nice diagram here at the bottom to remind us acids, low, near 0, 1, strong bases, strong alkalines, 13, 14, neutral, 7 in the middle. And it tells us the pH of some commonly occurring chemicals which we might come across. Okay, that is all the theory that we need to know for acids and bases. Thank you.